This is the Gravitational and Electric Fields Homework Booklet, question number 4. The diagram shows 3 students, each of mass 50 grams, standing at different places on the Earth's surface. So A is at the North Pole and student B is at the equator. Now, unfortunately, we have spotted a mistake in this question. It is just a typo really, and the power of 10 is incorrect here. So the mass of the Earth should be 10 to the 24. You would see this on your data sheet if you checked it there. So in the first part of the question, you're asked to find the gravitational force exerted by the Earth on the student. So here we just use the universal law of gravitation and substitute into the equation. So we have the gravitational constant, we have got the mass of the Earth, which we have corrected, and we have the mass of the student. And then dividing by the radius of the Earth, because the student is on the Earth's surface, making sure we acknowledge that that was given in kilometres. That leads us to an answer of 491 newtons. You can see here that the mass of the student was 50 kilograms, so a very rough estimation. We know we would expect the answer to be around 500 newtons. So that is how we spotted the mistake in the question here. Moving on, you are asked to draw vector arrows to show the forces acting on student A. Very important here that even though they haven't prompted you, that you do label these forces. So moving to the diagram, we're looking at diagram A here, and we can consider the person standing there, and the forces acting on them will be the weight and the normal reaction. These two forces should be drawn as the same size and should be labelled. While we're looking at this part of the page, I'll just jump to part B, question 3. You're asked to show an arrow showing the direction of the centripetal force on student C. Just be very careful to think about the motion of this student as the Earth spins on this axis. So the centre of the circle, as far as the person at C is concerned, is actually here. So you must have a horizontal arrow towards the axis as shown. Moving on then, this question now links with knowledge from circular motion. So it's a show that question. You're asked to show the linear speed of student B is about 460 metres per second. So straightforward use of the circular motion equation for linear speed and putting in the time of orbit as 24 hours, which we have converted to seconds here. It is important, since this is a show that question, that you record an answer to more significant figures than the value you are trying to show. This proves you have done the calculation fully for yourself, and it is often a requirement of the mark scheme on a show that question. Next, you're asked to calculate the centripetal force, so again relying on circular motion theory and considering the person at B, we have their mass, we have their speed squared, and we have the radius of the Earth. You could use the answer to 3 significant figures here if you wished. The final answer then is 1.66 newtons, and the mark scheme also allowed that to 2 significant figures. Finally, we get to the most challenging part of the question in terms of the concepts involved, so read the question carefully. So student B is standing on bathroom scales, and they're calibrated to measure weight in newtons. You are told that if the Earth were not rotating, the weight recorded would equal your answer to A1, which was the 491 newtons. Now, you are asked to state and explain how the rotation of the Earth affects the reading on the bathroom scales for student B. So first of all, consider the situation without Earth rotation. In that case, the reading on the scales would record the reaction force R. With no rotation, you can think about the weight of the person pushing down on the scales, and the scales pushing back with an equal sized force. However, the rotation changes the situation with regards to the forces. There would be a resultant force, which we would call the centripetal force. This centripetal force would equal the weight take away the reaction force. That's providing a net force towards the centre of the rotation. If you rearrange this equation, you can see that the reaction force would now be reduced. It would equal the weight take away the centripetal force. The centripetal force is what you calculated in the previous part of the question to be around 1.7 newtons. So the scale reading would be reduced by that amount.